interesting. So today I'm here in person. That Oleg is still taking a video, so we might put it up on our servers on YouTube or something. We have to see. So today we are here, but next time again we are not here, so we still have to see what we do. Maybe another video or substitute. So check Moodle for more announcements. So, I guess this is where we should continue on part 2. So last time we saw the basics of quantization, and this is basically where we will continue today. But first let me introduce some Linux commands. So as you know, everybody should have Linux on their computers or laptops. So I'm using Ubuntu because that's the most widespread version, but if you have other versions, that's fine too. They all work the same way, and if you have a terminal, they all have the same commands. Right? So that's a good thing. Basically, the operating system is basically the same. They only differ in the way that you have the graphics, for instance, how they look like. But the basics are still the same. And you will use mostly the terminal shell. Because that's the most basic and the most powerful basic. You can do everything using the terminal shell in Linux. And for that you need a few basic commands which you see here. So maybe you just saw me typing. So when you do, for instance, alternate control T, you will see that there's a terminal shell opening. And then you can enter commands in this terminal shell. Close it again, clicking this cross, so I already have the terminal shell here in the right directory. You can also increase the font size by using Control+. So it can be easier to see for you. It's smaller again. So an important command here is man, which is for manual entry. So this gives you a help function for commands. So that's very useful. For instance, cd. So cd is a command for which you can get manual help by just typing cd. You see there's no manual entry for cd. So that can happen too for some reason. So let's try another one. Command. PWD. So now we have a manual entry. So PWD is for print name of the current or working directory. So this is actually my next example. We have print working directory. So this basically tells you in which directory your terminal shell currently is. And then you can say cd to some other directory. For instance, when I use tab, I get auto-completion, and then I get all the example, then I get all the directories which are available. And then I can say, for instance, sample calculator. So now I'm in the directory sampling calculator. It's actually quite a nice example here. And then if I want to go up, I say cd space dot dot. So dot dot means I go one directly up. So now we are back. And if I say cd dot, what will happen if I just use the dot? Yeah, so dot is the current directory. And so if I say cd dot, nothing will happen. So dot is the current directory, and 2 dots is one directory up. So easy to remember. Yeah, PS is also what you need sometimes to see what processes are running in the background. Right, so here type PS, so trade running processes, and here you can see what's currently running in my terminal. So you saw me opening this LibreOffice, for instance, from this terminal. And this is what you see here. I use LibreOffice and then with an ampersand in the end, which means I put it in the background such that the terminal is still usable. And so this is now running in the background, and this is what you see, this process. So sometimes you have programs which are failing and still running in the background, and then you can use kill to end it. So in this case, you would use this number, say kill 3537, and then this LibreOffice will end. So if this, for instance, stops reacting, then this is a way to end it. And sometimes it happens if you have a broken program. This way you can kill it. I won't do it here because I want to continue on the slides, but this is how you could do it. Yeah, and sometimes you have processes which run in the background, but not started from your terminal. And then you can use the argument -EF. So E is something like extended and F for full, I think. So then you see all processes that run on your machine. So here you can see it. And you can see it's actually quite a long list. So these are all the processes which run on my machine, which is mostly operating system programs which are running. So basically everything that keeps my laptop running is listed here. So this is also sometimes useful if you have some broken programs to kill them, or sometimes also good to see if somebody else has started some program, or if a program is running correctly. If you want to have something started in the background, you can check if it actually is running. And so here it's good to know what program you're looking for, and that's why it's good to use the pipe. So here this vertical line is called pipe, which means you take this output, and instead of outputting it directly to your terminal, you put it into another program. So here the output is piped into the input of this command more. Does everybody know what more means? More basically takes any input and outputs it page-wise. So instead of overwhelming my little terminal, which has many pages now, I could use pipe. So this is L to control vertical line, and then pipe it into more, and then I get a page-wise output. So here's the first page, and then here you can see the sign more, and now it waits for the space bar. So if I now hit the space bar, I have the next page. So this gives you a page-wise output. And this also works, for instance, if you want to take a look at files in this web. You can say more file name, and then you have a page-wise display of the content of the file. So here, each time I push the space, you have another page, and if I push B, it actually goes back. So here it doesn't go back, it seems, but if you have a 5, B goes back one page. And then Q ends it. So here I have Q. So I could use, for instance, more on 02, 19. So this is actually my ODT file, which we are now seeing. And I could use more for this file. So what will we see if we take a look at it? What will we see? Say more a LibreOffice file.
Page by page display. Page by page display.
Page by page display of
The file. Contents of the file.
Yeah. So what do you guess? How does the content of the file look like? Will you see this text?
No.
What will you see?
Data.
Yeah. basically, we don't really know, right? It's, because LibreOffice is a format for word processing. So it should also contain, like, this is boldface, what font type we have, and all this extra information. So this file doesn't just contain the actual text, but also extra information, meta information about this text, how this text is formatted, what font we use, boldface or not, what date it was created, which is the author, and so on and so on. So actually I can try it. So now you can see, good morning. So you can actually see there's some strange signs here, right? So why is it those strange signs? It means there is some binary code which doesn't really have an ASCII correspondence. So here, some binary stuff which is not really representable. So another space gives me more of the content. And you can see here there's plenty of stuff, but it's hard to decrypt. So, yeah, it's all the same. Interesting. Yeah, so you cannot really read it because this is the format of LibreOffice. Yeah, but still you could use more to check what's inside, even though it's not a text file. Let's see if I have a text file. Yes, py. Yeah, for instance, our Python files, they are text files. So I could use this fraxi.py and say more fraxi.py. And then we can see the content of this program. And this actually makes sense. Right? This is actually the program that we entered. And this is also hence a good way to check your programs. Right? A quick way without opening an editor. You can just say more to see if everything is okay. So then there's actually also a command called tail. Do you know tail? Tail, instead of starting at the beginning, it gives me the end. And so I say tail, taxi, so these are just the last lines of my program. You see here it ends with return. So sometimes you just want to see the end of some file, and then this is convenient. You don't need to scroll down until the end, you just use tail. Yeah, so kill I just said, you end a program, a kill program. df sometimes is useful to show how much free disk space you have. So if I type df, then it shows me my free disk space. So most interesting is usually slash. So here this shows you the total capacity of your hard drive. So right now you can see I'm using 13%, so plenty of space left. But if you say having 95%, then you should clear some data on the left. Right? So anything above 90%, you should remove some data so that you stay below 90%. Otherwise, you overflow your disk drive. Yeah, then du is disk usage. It shows the memory used in your current directory. So this is useful for cleaning up. So for instance, if I type du in my directory, here you can see the space used for each directory, and here's the total space in, I think, bytes. Bytes or kilobytes, I'm not sure. So to make that clear, you can type du minus h for human readable, right? So now you get it in human readable form. So now it's 957 megabytes. So what we saw before was kilobytes. So this is good for checking which uses the most memory, and then if you in this way you can find large files, and if you don't need them, you can delete them. You need to clean up your computer. Yeah, who am I is useful if you log into other computers. Then you can see your username. Who am I? So who am I? Sure. Correct. Yeah. Date shows you the date and time. Date. So this sometimes is useful to check the system clock and also to use in programs if you want to type them. Time you can use to measure time of a command. For instance, time ls tells you how long it took to execute the program. Something like this. Top shows you how busy your system is. So here I just executed top. And then you can see here the processes, and here the CPU percentage, and here the memory percentage. So that this again is something useful if your system, your laptop becomes very slow. Here you can check which process is responsible for the slowness, for instance. So if you have something which uses a lot of memory, that means you have a lot of swapping going on, and that slows the system down. So avoid high memory usage. And also if the CPU is very high, then this means that it's very busy. And so if your CPU is very high, then it shows it computes something. Yeah, NV is very useful for move. This you can use to change a file name or a directory name. So move all directory name, new directory name. Or move old file name, new file name. RM is for remove the file. Make dir creates a directory. So make dir file name creates this directory in the current directory. cat is for concatenate. It takes the output contents of a file or several files. So similar for as for more. So here you can say cat rexy. So again, it shows you the output, but now without the space bar. And you can also do that for several files. So let's see, this is P9 and rexy.py and then say LMS example. So now basically it concatenated those two files. So it first printed out the first one and then immediately after it the second one. So this is useful if you really want to concatenate two files. Then you can say, for instance, cat those two, and then you pipe it into some output. For instance. So you have those two files, you are concatenated and output in this new file. So if you have a few pieces that you want to append, this is where you can do it. So without having to open an editor. More we just saw. Xterm starts in the terminal. So this is basically a way without doing it using keyboard shortcuts. You just say Xterm. Keyboard shortcuts. You just say Xterm. Ampersand. And then you have new terminal. Starts with tiny font. Control plus. Oh, Control plus doesn't work. Interesting. The Xterm actually gives you different terminal. There are actually different terminal types. So this is one type. You can actually see when you look at the iPad and you click about. This is Mate terminal. This is one extra. Which gives you the path to a command. For instance, which ls. So this shows you where in the operating system the command ls is in. So you can see it's located in bin ls. So this is also very convenient and useful in Unix or Linux, that all commands are files located in the directory somewhere. Right? So basically, when you type ls, then the machine searches in its so-called search path for this command. So bin is in the search path of the machine, and there it finds ls as executable file, and then it executes this command. So this also means I could modify those commands by just changing this executable program here. So this means basically the entire operating system is accessible and modifiable. Quite different from Windows, for instance. They don't let you go there. But in Linux you can, because it's open source. So in this way, you can find the path to any command that you use. For the usual Linux command, it doesn't really make sense, but for instance, if you make your own programs and put them somewhere, right, somewhere in the search path, and you want to check where you actually put it, then you can use which to type your executable name and then remember where it was. Yeah, shutdown actually lets you shut down your computer without using your on-off button. So this might be useful if your machine is stuck except for your terminal, then shutdown now shuts down your computer. VI opens a terminal inside an editor inside your terminal. So you type VI, for instance, then you get an empty terminal line, and you can use, for instance, the key I, and then you can type something. This is a test. And then you can store it. You get out of here by using escape, and then you say Control X. No, it was exclamation mark.
QW.
Huh?
QW.
QW. I see. So escape.
But now you have nothing.
So you need to, like I for insert, you can type something, and then you get out by using escape. Right?
Yeah, and then.
So now exclamation mark, it's not working.
Colon.
Colon.
Yeah. QW.
QW.
Oh, WQ. So write and Q. Quit.
Q.
No. W for write and Q for quit.
Q exclamation mark. I don't want to write, remember?
Ah.
W is for write, and then it asks you for a file name, but I don't want to write it because it's junk anyway. So Q is for quit, and it doesn't let you quit if you didn't write it first. But if you use exclamation mark, QW, Q exclamation mark, then it lets you exit without writing to file. And this colon means now now you want to enter a command. Right? So to exit the entry mode, you have to hit escape, the escape key. Then you enter command mode, and then you enter colon to enter your commands, short commands like Q, exclamation mark. It works. Actually, what I find much easier to use is nano. So this is nano, right? Because here you have all the explanations of the shortcuts, and also you don't have those two different modes, like entry mode and command mode. Here you just have one mode. Here you can enter stuff, and also then you use Control X to exit. So here Control X. Now it asks me save modified buffer, and I say no, and I'm done. So I find now actually more convenient than VI. Right, so here I also added a few explanations. So maybe I should also enter nano. Mode. So this is a singular editor for German. Yeah, useful is also SSH. Do you all know SSH? So SSH is, for instance, if you have compute-intense programs that you want to run on a different computer. For instance, you have a machine which has many GPUs and you want to run a big neural network program for training, then you cannot do it on your laptop. So you have to use some big machine at the university, and you know the machine name, and then you have to use SSH to log into it. So you would do SSH and then machine name. .to Ilmenau. Right. And then you say return, and then it says could not resolve because it doesn't know machine name. Right. But this is how you can then log into the machine and ask you for your password, and then it appears on this terminal. So, and then you can use this terminal as if you were sitting at this machine. So this is very convenient, and one of the big benefits of Unix and Linux that it has all those networking capabilities built in, and they are very sophisticated. And that's also why many of the big servers, network machines are usually based on Linux, Unix. Yeah. Then you have SCP, CP and SCP. CP is for copy. This is where if you want to copy a file from one part of the directory to another part, not move, but copy. Right? Then you have two copies of it. SCP is secure copy. Then you can do the same as CP on your local machine. You can use SCP between a remote machine and your own machine. So this is between network machines. So for instance, if you're done training the neural network on the university machine, you want to copy the weights back to your laptop. And you could do that by SCP. So you use SCP, then user at remote machine, and here the directory, and in this way you would say dot for your local directory here in the end. So it always copies from here to there, or here it copies from your local machine, everything in your current directory, it copies to the local machine. So it's also very useful to copy files or even directories between local machine and your own machine. chmod is important to change the mode. If you want to make an executable file that executes when you double click, you need to change it to executable. So you would do it by chmod user group plus x for executable and then file name. So for instance, if you have a Python file, for instance the fraxy.py, and you want to make it run by double click, you need to make it executable. So this is how you would do it. So chmod ug plus x and then fraxy.py. And that makes it executable by double click. Yeah, Ifconfig It's useful if you want to access your machine from external. If you want to access your machine from external, from some other computer, this shows you the local IP address. So in my terminal I can type Ifconfig, and here it gives me information, and here you can see my internet address. So this is my internet IP address, and I have OpenSSH server run on my laptop, and that listens to external requests for SSH. So that means if from externally, from somewhere in the world, I type SSH and then this address, I can log into my memory. So this is also useful for, say, if you have a machine at the university, you sit at this machine, you type Ifconfig, then you get this address, and then when you're home at your laptop, you can type SSH, this IP address, and then you can log into this machine. If on this machine is OpenSSH server running.
But it works only if this address is global, not local.
Yeah. This is a global address here in the university, but if you sit at home, then you get a local address because the DSL router maps its own unique global address to many local addresses. That's something that's a problem of Internet IP4. It runs out of addresses, and that's why every DSL router only gets one IP4 address. And if you have several machines or laptop, smartphone, then they all need their own IP4 address, and that's why it creates a local IP address. So if you want to try this at home, so this works between machines at home. So if you have two different laptops, you can actually use it to network between those two different laptops, but it doesn't work from externally to your laptop. But here, within the TU Ilmenau network, it works, because the TU Ilmenau has many IP addresses. So they are not just the router, they are actually a big institution in the internet. So, SOX is also important for us because it contains audio tools. So you need to install it using sudo apt install SOX, and then it installs this library of tools. It contains, for instance, the play command for playing an audio file. It also contains record for recording audio. Yeah, this is kind of like a hacker's tool. wget copies an entire website to your local machine. I think Snowden used this to copy all the content of the CIA. Yeah. So here you can basically copy entire websites, including their fields. Yeah, debugging is also important. It's actually essential part of programming. And an essential strategy for it is divide your program into several simple functions. It's called divide and conquer. Right? If you have something complicated, make it simple. Subdivide it in simple subtasks. Yeah, and for those simple subtasks, you need to know the input-output relationship, and then you can test it. Each of them separate. Give it an input, test if the expected output result. Right, and for that I actually like to use print statements. For instance, using print statements in Python. So print is the most simple. It works always, and yeah, it's probably the easiest for debugging. Yeah, questions to Linux programming. So everybody should have it on their laptop now. And yeah, don't forget this sudo apt install. So that installs your software you need, or sudo pip install to install libraries for Python. PIP for Python, packet installer for Python.
Python installation package.
Python installation package. Oh, okay. Yeah, so back to quantization. So we saw we have different ways to do the quantization, like mid-thread, and mid-rise, and we will actually see more versions. But first, let us try to find out what's the signature-noise ratio for our quantizer. So assume we have some A to D converter, analog to digital, with n bits, capital N bits. What's the resulting noise, signature noise ratio, where noise is the quantization error? Yeah, so SNR is defined as the ratio of the expectation of the signal power to the expectation of the noise power. So, and we already had, we computed that we have the expectation of the noise quantization power is delta square over 12, right, where delta is the quantization step size. So for the SNR, we just need to have the expectation of the signal power, and for that we need the probability distribution of it. I'm not sure, did I actually show it in the video, this piece already? Do we already know this? No? Yeah, so it's actually when we have this very simple case of a uniformly distributed signal, which means all amplitudes appear with equal likelihood, all signal values, then it basically looks like our quantization error. So now instead of quantization error between minus delta over 2 to plus delta over 2, we have a signal which goes from minus A over 2 to plus A over 2, where A is some amplitude of the signal. Right, and then we can use the same calculations. So here's our signal, here's the assumption of uniform distribution. Then we can use the same calculation, and we end up by A squared over 12 as the signal power. So this is the average or expected signal power. And yeah, what signals have this property? Basically, if you have noise, random noise, then we have this uniformly distributed random noise has this property. Speech or music in general has a non-uniform probability density function. It's usually a Laplacian distribution, which is P, which means small values are by far the most likely. Yeah, another example for a uniform P would be a triangular wave. You can see that each value is equally likely because this basically rises through every value with equal space. Right? So it passes every interval here within the same time span. So that means you get a uniform distribution this way. Same for a sawtooth wave. Right? You can also see basically the same speed for every interval. So that means we have an SNR of signal power divided to quantization error power. Here the 12 cancels, so what's left is A squared divided by delta squared. And now we can reformulate it into the number of bits that we have. So we can, instead of using delta, we use the number of bits. And we know if we have n bits, we have 2 to the n intervals, 2 to the n quantization intervals. And that means we obtain delta by just dividing our range from plus A to A over 2 to minus A over 2. So we have range of A and divide it into tuple-lane intervals, and just substitute delta by this expression. So then you get this result, the signal-to-noise ratio. Here this A cancels, and what's left is 2 to the 2n. So now you have 2n, basically the square because you have a power. So now we can turn this into the B. So this is the power ratio, so we need to use the 10 here before the log 10. So we have 10 log 10 of 2 to the 2n. So what's the exponent of the log goes into the front here. So then we have 10 times 2n is log 10 of 2. Log 10 of 2 is roughly 0.3. Right? So then as a result, we have n times 6 dB roughly. So this shows if we each bit more, so if we increase n by 1 bit, then we have 6 dB more SNR. And then this is the rule of thumb, that each bit more gives you 6 dB more SNR. So if we go from 7 to 8 bit for our A to D quantizer, we gain 6 dB in SNR. So it's easy to remember, right? Easy rule of thumb. Yeah, but here we assume that we really use the full range of our quantizer, and often you want to avoid overloading your quantizer, and that's why you reduce the range. Basically stay away from the boundaries of the A to D conversion. So the signal usually is actually not full range. So what happens in this case? Assume we have a reduced amplitude, A divided by C, and C is some factor larger than 1. And this is our new SNR, and you can see here we get our old SNR divided by C squared. So our SNR is reduced, or in dB, we get our old expression minus 20 times log 10 of C, which makes sense because C squared was in the denominator, so now it appears as minus the log here. So basically what we get is now n times 6 dB minus 20 times log 10 of C. So basically this is the C expressed as dB. Yeah, so if you say, if you're 10 dB below full range, then your SNR is reduced by 10 dB, by exactly this 10 dB. Right. So it's also easy to remember. Yeah, example, this is the famous example for the CD. We have a 16-bit quantizer. This is the audio CD format, 16 dB, and in this case of the uniformly distributed full range audio signal, we get 96 dB SNR. But keep in mind, this is only the ideal case. So usually you want to stay below full range, and then this becomes less. So for instance, if you stay 20 dB below full range, yeah, which means we have only 1/10 of the full range, then this goes down to 76 dB. Yeah, and this shows also why it's important not to make the safety margin to full range too big. Yeah, so what happens if you don't have a uniformly distributed signal, say speech and audio signals, which are modeled by Laplace distribution, or the Gaussian mixture model, or even a simple sine wave. So we can take a look at the PDF of the simple sine wave. So here's the sine wave, which are plotted using this little code snippet here. And here you can see that the different intervals of the amplitude are not crossed with the same speed, so to say, like between small intervals. And here you have constant time going up. Then you can see it crosses quickly here in the low values, and here it slows down in the end, right? And then it turns around. Again, here it's fast speed, and then here it's becoming slow and turns around. So you would expect the probability being in this range to be low, and the probability being in the end higher, right? Because of this behavior. Yeah.
Previously, you saw the sawtooth wave. Yeah, in that there's a constant rise, then there's a sudden dip.
Yes.
But that cannot be a non-informed distribution.
No, because you have the same speed for each interval.
Okay.
Right? When you have constant time for the sawtooth, it was having a constant speed going up, constant speed going down, constant speed going up. So basically, it depends on the slope. If the slope is the same for all the values, then it takes the same time to cross each small interval. Right? Here you have a case where the slope is changing. Right? So here you have a high slope, so it rises quickly when you have constant time. And here the slope flattens and now becomes even at the end points, even becomes horizontal. So it stops basically. Right? So when you take actually derivative, then at this point it would take like infinite time to cross it. Not really infinite, but the density would be infinite. Right? So that's different here. Yeah, so let's go to the next one. Yeah, so here we again have our sine wave. Yeah, you can actually calculate the PDF of the sine wave using this derivative, and you will end up with this formula. And then you see here actually for x equals 1, this becomes infinite, also for x equals minus 1. So x is the amplitude value. So here we actually take the derivative and then the inverse function, and this is how we end up in this with this equation. Yeah, so yes, you can see how you can obtain it. So x is our amplitude value, and that's the inverse of the inverse function. So we have a given bin in x. Let's see. Actually, y is the amplitude value here, and then x would be the time, I guess. And then you can take the derivative, and you get the result. But I don't want to go into the details here because it doesn't really matter, and we actually take a different approach. So here we see that we have a PDF which actually is infinity at plus minus x. Yeah, so you're kind of stuck here using the PDF at this point because it's difficult to find a closed form solution for this 1 over square root 1 minus x squared. Right? It's difficult to solve. And then we take an engineering-like approach. If one direction turns out to be too difficult, we try something else. And this is what we do here. So the alternative solution is to look at the sine function and see that it's not a probabilistic function unlike a random signal, but a deterministic function. For each time, we know exactly the value, and we also know the period. Right? So in order to compute the power of the sine, we just need to integrate the power over one interval, over one period. So basically what we need is this. So we have the sine function. If we want to have the power, we square the sine function. So we assume the sine is something like the voltage, and we have a 1 ohm resistor, then sine square will be the power. And we do this over one interval because we're interested not in the total power, but the average power. And then hence we divide by 2 pi. That's the length of one interval that we have. So we can also then, to simplify this integral, we rewrite sine square as 1 minus cosine 2t. Do you know this equivalent? So this is one of the sine equivalents. And this is actually easier to integrate because it just contains a cosine. So 1 is easy to integrate, cosine is easy to integrate. Yeah. So what's the integral of the cosine of 2t over t equals 0 to 2p, 2 pi? What's the result? 0, right? Because this goes up and then it goes down the same, so they all cancel out. So here this becomes 0. Right? Because it's above 0 as much as it's below 0. So what's left from this integral is basically the 1. So what's the integral over 1? It's 2 pi, right? So it's the length of the integral. So we have 2 pi divided by 2 pi, and that's 1. Except we forgot the division by 2. Right? So the result is 1/2. No, not pi. 1/2. So the pi cancelled here. So what's left is 1 divided by 2. Yeah, so this is the result. 1/2. So this is our average power over one period. Yeah. So if we have a sinusoid, say, a over 2, like our previous example, a over 2 was like the range from 0 to plus, and then we have the same for the negative. Then the expected power would be a squared, a over 2 squared, and another half here, so we would have a squared divided by 4 divided by 2, so we would get a squared over 8. Make sense? Yeah, this leads us to a signature noise ratio of a squared over 8 divided by delta square over 12, assuming a full range sinusoid. Here we can cancel some factors and we have 3 over 2 times a squared over delta square. Right. Again, using then, instead of delta, using the number of bits. Or instead of a using the number of bits, we can replace a by 2 to the n times delta. Here we can see we get this expression and the deltas then cancel. And what we get is 1.5 times 2 to the 2n. And again, turning it into a dB number gives us our n times 6 dB that we had before, but now plus 1.76 dB. Kind of interesting, right? Usually now higher than before, higher than for the uniform case. And that is because the sinusoid has this PDF which emphasizes the high values. Right? And this gives us this boost of 1.76 dB if we have a full range sinusoid. But again, this is kind of unrealistic. Yeah, so that now leads us to compending. Does everybody know what compending means? Very good. Yeah. So that's what we're doing here, right? Before quantization, we first do compression of our signal range, and after dequantization, we do an expanding of our signal range. And in this way, we should get a more equally distributed signal-to-noise ratio. Remember when we reduced our range? Remember when we reduced our range of our signal, and we made our signal smaller to avoid clipping, then we have a loss in SNR accordingly. Right? So that means small values get a worse SNR than large values. If you have your, say, music signal and you have some very soft passages, these soft passages get a very bad SNR. And this is actually also a problem, for instance, if you use the CD and you have classical music with very soft passages and you turn up the volume, then you might hear quantization noise. And this is the problem that compending tries to solve. Compending basically enlarges those small passages, those small signal values. So all small values are amplified, but the large values are left unchanged. And in this way, you should get a better SNR for small values. And this is actually most used for speech coding, because in speech coding, at least traditionally, often only 8 bits per sample was used. And then the quantization noise becomes really noticeable for soft pieces of your signal. So what's the SNR for 8 bits? Signal to noise ratio?
48.7.
Yeah, roughly 48. So it's much lower than the 96 or the CD. And this 48 is only true if you have a full range speech signal. So as you know, speech fluctuates a lot. And that means you get a lot below this 48 when speech is not full range. Right? And then really the quantization noise becomes noticeable. And that's the problem that compending is solving. It basically amplifies those small signal portions. Yeah, so first we apply a nonlinear function, our compression function, to the signal to boost small values. Then we apply a uniform quantizer, and on the decoding side, we first apply the inverse, or the dequantizer, the reverse, I should say. It's not the inverse, the reverse. And then the inverse nonlinear function. So that's the expansion function. We reduce small function values, we reduce small values again to restore their original size. Expansion. So this is how it looks like. First we have our function, our compression function, then we quantize, then we dequantize, and then we have our inverse, the expansion function. And a standardized method for compending is the so-called mu law and a law. And they were actually used for speech coding for ISDN lines. Does everybody know what ISDN means? So it was like a few decades ago for digital telephone lines where 8 bits per sample at 8 kilohertz sampling rate. So they have 64 kilobits per second. So this was the standard for transmitting speech over those lines at 64 kilobits per second. So this is here the compression function. And you can see U is the value that comes out from compression. X is the original speech signal, for instance, and mu is 255. And that's where the mean came from. So this is fixed. That also means that this denominator is fixed. So this is your compression function, And x is expected to be normalized between 0 and 1, which means this is only for the magnitude. Okay. So if you have a speech signal plus and minus, so before putting it into this compending function, you separate the sign, plus or minus, and keep the magnitude. And then the magnitude is put into this function. Right? And the sign is kept separate. An alternative is the so-called A-law compending. Here the formula is actually quite similar, except that the 1 is missing. Right? And they also distinguish, hence they distinguish for small values. So this is the formula for x larger than 1 divided by a, and this is the formula for between 0 and 1 divided by a. In effect, they are quite similar when you look at the functions. Here you can see those functions. Let's see. Here's a law and u law. That x-axis now is between minus 1 and 1. As you can see here, in the big picture, they actually don't differ. It's basically the same. But if you zoom in the area between minus 0.05 and plus 0.05, you can see slight differences. Here's the mu law, and here's the a law. So for all practical reasons, it doesn't really matter. Yeah, so this compression function is applied for our uniform quantizer. Here's now an example. So we have an x between plus a and minus a. And what you would do then is you take the magnitude of x divided by a and put it into this formula. Right? So you take magnitude and normalize it to the range between 0 and 1. And yeah, so here I put the sign of the x in front of it, so that y is the compressed value with an index. And this is what you would transmit. Yeah, this y is then quantized. So here I have a, what is it, mid-tread or mid-rise? Still remember? Yeah, it's mid-tread. Right? Round means mid-tread, which means small values are always rounded to 0. Yeah, so y now has this range between minus 1 and 1, so this is the compressed value. It is also made to be in the same range, right? This is how the formula was designed, to have the same range as x. So this is including the sign. And hence if you have 8 bits, like in the case of the speech coder, we get this delta. So here, delta is 1 divided by 2 to the 7th. So this is including the sign. And so we get an 8-bit code word in this way, including the sign. And in the decoder, we take the index and multiply with this quantization interval q or delta, as we named it before. We get a reconstructed value after dequantization, and then we need to apply the inverse function, the expanding function. Right? So far we only saw the compression function, so now we need to derive the expanding function, which we can do with a few steps. Right? So here you can again see the compression function, and then we use a few steps to get x back, right? Or magnitude x. So this is what you can see here. So 256 to the power of magnitude y minus 1 divided by 255 times a is magnitude x. Right? And then we just need to add the sign, and we get our dequantized value x after compending, after next value. Make sense? Do these steps make sense to you? Okay. Yeah, so here actually in the decoder this y is y rec, the reconstructed, and this x will be the reconstructed x. Yeah, so this is now our dequantized value, so the decoded speech basically, and as a result, our signal to noise ratio remains approximately constant. Yeah, so large single components have large effective step sizes because compending, and larger quantization errors. And small signals have smaller effective quantization step sizes and smaller quantization errors. So that means the SNR more or less constant over a wide range of amplitudes, which was our goal. Yeah, so basically this approach is identical to having non-uniform quantization step sizes because of this compending. Do you have questions? Yeah, so the compression and expanding of the signal makes the step sizes, the uniform step sizes, look like relatively smaller to the signal. It has more quantization steps to cover. And this has the same effect as a smaller signal with smaller quantization steps. So here's a Python example for a Wiener Quantizer. So we first listen to the uniform mid-thread quantizer using our Python script and make sure the part of the mid-thread quantizer is uncommented. So now I can use my terminal to open this program to make sure that the mid-thread is uncommented. Control P. Edit. Yeah, so here's our little program. So does this first part here make sense to you? So here I'm importing the necessary libraries. So if you execute this file, so you should also try it at home on your laptop. And if you get an error message, library not found, you need to install it using sudo pip and then this name, pip install and then the name of what you need. Yeah, for instance, Pi Audio. Right? Pi Audio is not installed by standard. NumPy should, structure 2, so the rest should be no problem. So here's the sampling rate I'm using, 2 bytes per sample from the sound card. So this is for the sound card setup. And I'm reading 5,000 samples from the sound card as one chunk, as one block. Here I'm making the object for the audio card. And here I'm using the open command from this object to access a stream from the audio card. So now the audio card is open for us to read sound. And this is what I'm doing here in the for loop. I continuously read blocks from the sound card and then quantize it. So let's go down here. You can see here I'm now reading a chunk from the stream, get data. So this is byte data, so I need to convert it, and that's what I do using struct unpack. So H means byte data, so 16 bits per integer. And this is the number of bytes we expect. And this is the file or the array from which we convert it. And it converts it to short floats. Right? So short floats is, I think, 32 bits. If I'm not wrong. And then I convert the short bits, short integers to floats in this line here. Because floats are easier to compute. Yeah, and then we can do the quantization. Here I'm using quite a large quantization step size to show you the effect. So here we have a full range between minus 32,000 to plus 32,000 because we have 2 byte samples, 16 bit. And that means 4,000 is a considerable part of this range. So it's quite a coarse quantization for the demo here. So then here we do the mid-thread quantization using rounding. So here samples divided by Q, and here the dequantization indices times Q. Right? So these are reconstructed samples. And then I basically make sure that we don't have clipping. So I do clipping here. And then I turn it back into integers, turn it back into bytes in this line, and then write the bytes back to the sound file for us to hear. So I have a Bluetooth speaker, which I should use for this demo. Let's see where it works.
Bluetooth mode.
Bluetooth mode. So maybe make it not too loud. And now execute it using Python. So at home you should do the same and try it on your laptops. The same way I do it here. So now we should have mid-thread quantization. Test. Very long. Maybe I should make it a little softer. I couldn't hear much quantization, would you? Didn't sound too bad. Maybe that's because it was so loud. Maybe I need to. So here we have the sound settings. Did you see where you did the sound settings? Yeah. So if you do the left mouse click on the speaker symbol and go to sound settings, then you can go to the sound preferences. With hardware, you can select the desired sound device, and you can test the speakers. Oh, it's actually very slow. Oh, it's the wrong speaker. Could you hear it? Maybe I need to make it a little louder. So here's the output volume.
Front, left, front, right.
That's better? So then we can also check the input. So here we have the input, and you can also here see the range of the input signal. So here you should also be careful to not overload the input, so it shouldn't go all the way to the right. But you should see some wiggling here. Right? If you see nothing here, then there's a problem with the microphone input. Or if it's too low, like here I'm hardly seeing anything, then it's too low. So range like this is actually best, so that you have it in the mid-range. So before making this experiment, make sure that you check the output, the sound output, the hardware, and the sound input. So now I'm trying again. Test. Still so loud, right? Maybe that's my Bluetooth speaker. So this is a test. Can you hear the noise? So especially in the like in the breaks between when I'm speaking. Crackling sound. That That's the quantization unit. Okay, so that works. So here, when the input is too small, actually everything disappears. Right? Basically, the small values are rounded to 0. And now we can use, as comparison, this mu-log quantization function. So I'm also opening here. So now it's the one with the mu log. Right, and here you can see how the mu log quantization now is implemented. So here you can see our formula, the mu log formula that we saw before. Here you can see the normalization. So I divide by the amplitude. So to make sure that this is between plus minus 1. Here x makes sure that this is just positive values, and the sign here is separate now in front of it. And so now y contains the companion value, the compressed value. Here I'm doing the mid-thread quantization on y instead of x. So now we get new indices. Here's the dequantization, and here's the inverse, the expansion function. So here, this function and the compression function is now there in addition. And then here's this is the same stuff as before. So now we can try this function and compare it from what we had before. Okay. Other questions to this problem?
Sir, that amplitude, where can I get this amplitude value?
Again?
32768.
This one
Yeah,
here.
yeah. Where can I get this amplitude?
It's 2 to the 15th. Right? Because the range, we have 16-bit audio. Right? The first bit is sine. So what's left is 15 bits for the magnitude. Right? So, and 32,768 is 2 to the 15th. So you can actually check it by going to Python. So here you can type Python to go into interactive mode. Python. Did you know this?
Yeah.
So if you just type Python without any this?
Yeah.
So if you just type Python without any try, it goes into interactive mode, which you can see here, the 3 triangles doing that. And then you can use it like trying out commands or computing 2 to the 15th, for instance. So for that I need mathematical functions, so I need to type import numpy as np, and then I can write, actually I guess I don't even need it, 2 to the 15th, right, 32,768. Make sense? So when I say then quit, I go out from this interactive mode. So now I can execute this program, this demo program. So I need to be quiet to hear the demo. Okay. 1, 2, 3. 1, 2, 3. Test. Sounds the same somehow, right?
I think that noise is earlier that
Yeah. So we can compare it to the previous one. There seem to be no noise. So compare with this. 1, 2. There's less noise. Could you all hear it?
Yes.
So in this case of new law, we have less noise than in the case without new law. And that's the purpose of it. To have, especially in the soft passages, to have less noise.
This program is written for 8-bit quantizer or for
Yeah, this new law is usually made for 8-bit, but here you can do whatever you want. So here, that's actually a good point. I can set the quantization step size here. So here, in effect, this is just 16 steps, so this would be 4 bits. So that's also the reason why you could still hear the noise. So if I go to 8 bits, 8-bit, it would be 64, right?
256.
Right. So let's try 256. So now new law with 8 bits. 1, 2, 3, 1, 2, 3. No noise. It's completely gone. High quality speech. Yeah, this is actually also experiments that you can do at home. You have those Python programs in Moodle so that you can download it and also modify it. Play around with those step sizes and okay, I guess time is over, so thanks for your attention.